You have already learned that if there is no change in the state of a body, its temperature increases when it absorbs heat energy from the surroundings and decreases when it emits heat energy. Now let us study the factors that influence the heat required to change the temperature of a body. Consider a given quantity of water being heated using a source that supplies heat at the rate of 100 joules per second. If the initial temperature of water is 303 Kelvin and the temperature is increased to 308 Kelvin at the end of 3.5 minutes and to 313 Kelvin at the end of 7 minutes, the amount of heat absorbed for a rise in temperature of 10 Kelvin is double the amount of heat absorbed for a rise in temperature of 5 Kelvin. This means the quantity of heat absorbed or emitted, delta Q, by a body is directly proportional to its change in temperature, delta T. Let this be equation 1. Heat capacity denoted by S of a body is defined as the heat absorbed or emitted per unit change in its temperature. Therefore, S is equal to delta Q by delta T. The SI unit of heat capacity is joules per Kelvin. In the experiment shown earlier, heat absorbed by the given quantity of water in 7 minutes can be expressed as delta Q equals to RT. Substituting the values of R and T, we get delta Q equals to 42,000 joules. The corresponding rise in temperature, delta T, is 10 Kelvin. Substituting the values of delta Q and delta T, the value of heat capacity S is 4,200 joules per Kelvin. Now let us double the quantity of water. Then the time required to raise the temperature from 303 Kelvin to 308 Kelvin is 7 minutes. This means when the mass of water is doubled, the heat required to raise the temperature by 5 Kelvin is also doubled. Hence, the quantity of heat, delta Q, required to raise the temperature of a body depends on its mass also. Therefore, delta Q is directly proportional to mass m. Let this be equation 2. From equations 1 and 2, we can write that delta Q is directly proportional to m delta T, or delta Q is equal to S m delta T, where S is the specific heat capacity of the substance. Specific heat capacity is the quantity of heat absorbed or emitted by a unit mass of a substance for a change in its temperature by 1 unit. Specific heat capacity S can be expressed as S equals to 1 by m into delta Q by delta T. The SI unit of specific heat capacity is joule per kilogram Kelvin. Specific heat capacity depends on the nature of the substance. Different materials have different specific heat capacity values as shown in the table. The specific heat capacity of water is 4,186 joules per kilogram Kelvin. For practical purposes, we can take the value to be 4200 joules per kilogram Kelvin. Water is used as a coolant in automobile radiators because of its very high specific heat capacity. The specific heat capacity of a substance also depends on its temperature. Different amounts of heat are required for a unit rise in temperature of a unit mass of a substance at different temperatures. For example, the variation of the specific heat capacity of water with temperature is as shown. This is why a specific temperature range is given in the definition of calorie, which is a general unit of heat. A calorie is defined as the amount of heat required to raise the temperature of 1 gram of water from 14.5 degrees centigrade to 15.5 degrees centigrade. Sometimes, it is more convenient to describe the quantity of a substance in terms of moles, mu, rather than mass, m. When a given substance is expressed in moles, its specific heat capacity is known as molar specific heat capacity and is represented by C. The molar specific heat capacity of a substance is defined as heat capacity per mole of the substance. This is given by C equals to S by mu equals to 1 by mu into delta Q by delta T. The SI unit of molecular specific heat capacity, C, is joules per mole Kelvin. Molar specific heat capacity also depends on the nature and temperature of the substance. The definition of specific heat capacity is applicable for all states of matter, namely solids, liquids, and gases. But for gases, the heat required to raise the temperature depends on the process involved. If we heat a gas by keeping its pressure constant, then the heat delta Q required to raise the temperature of 1 mole of gas by 1 unit is called its molar specific heat capacity at constant pressure and is denoted by Cp. Cp is equal to 1 by mu into delta Q by delta T at constant pressure. The molar specific heat capacity at constant volume, denoted by Cv, is the heat required to raise the temperature of 1 mole of a given gas at a constant volume by 1 unit. Cv is equal to 1 by mu into delta Q by delta T at a constant volume. Let's take 2 iron rods, A and B, at 2 different temperatures, and place them in a thermally insulated box and make sure they are in contact with each other. We know that heat energy flows from a hot body to a cold body. Since they are in a thermally insulated box, no heat escapes to the surroundings. Heat energy emitted by the hot body must be completely absorbed by the cold body. Even when more than 2 bodies are placed in a thermally insulated box, some bodies lose heat energy and other bodies gain heat energy. The total heat energy lost by the hot bodies must be completely absorbed by the cold bodies. This means when 2 or more bodies at different temperatures are brought into thermal contact, and if no heat is allowed to escape to the surroundings, then the total heat lost by the hot bodies must be equal to the total heat gained by the cold bodies. This is called the principle of calorimetry. Calorimetry is the science of measuring heat. Heat gained or lost by a body is expressed by the equation delta Q equals the product of M, S and delta T, where M is the mass of the body, S is the specific heat capacity of the body, and delta T is the change in temperature of the body. For example, an apple of mass 0.2 kilograms and specific heat capacity of 3640 joules per kilogram per Kelvin is placed in a refrigerator. If its temperature is changed from 30 degrees Celsius to 10 degrees Celsius, find the heat that flows out of the apple. Given that mass M equals to 0.2 kilograms, specific heat capacity S is equal to 3640 joules per kilogram per Kelvin. Change in temperature delta T is equal to 30 minus 10, which is equal to 20 degrees Celsius. Heat that flows out delta Q is equal to the product of M, S and delta T. Substituting these values and calculating, we get delta Q equal to 14,560 joules. In calorimetry experiments, a device known as a calorimeter is usually used to make heat measurements. A calorimeter consists of a small metallic vessel with a stirrer, and usually both are made of copper. The vessel is placed in a wooden box with insulating material surrounding the copper vessel in the box. This wooden box acts as a heat shield and reduces heat loss. There is a wooden lid on the top of the box, where there is a provision to place a thermometer and also to pass the stirrer through. Let us find the specific heat capacity of a solid using the principle of calorimetry. To do this, a Reynolds apparatus and a calorimeter are used. As we use water in the calorimeter, we need to take a solid that is denser than water and insoluble in water, say a metal ball. First, the calorimeter with stirrer is weighed using a physical balance. Let its mass be M1. We now weigh the material used in the activity, that is, the metal ball. Let its mass be M2. Pour sufficient water into the calorimeter. And then the mass of the calorimeter and water is found to be M3. Then mass of the water is equal to M3 minus M1. Note the temperature of the water. Let it be T1. Now, heat the metal ball in the steam chamber of Reynolds apparatus till the thermometer in the apparatus shows a steady reading for a few minutes. And let the temperature of the metal ball be T2. The wooden partition separating the steam chamber and the calorimeter provides thermal insulation to the calorimeter from the chamber, so that there is no transfer of heat from the chamber to the calorimeter. Now bring the calorimeter below the sliding base of the steam chamber and slide open the base of the chamber. Drop the metal ball into the water in the calorimeter and stir the mixture for some time. Then note the equilibrium temperature T3. Let the specific heat capacity of the copper metal ball and water be S1, S2 and S3 respectively. Here, heat is lost by the hot metal ball and gained by the cold calorimeter and water. Heat lost by the metal ball is equal to M2 into S2 into T2 minus T3. Heat gained by the calorimeter is equal to M1 into S1 into T3 minus T1. Heat gained by the water is equal to M3 minus M1 into S3 into T3 minus T1. Applying the principle of calorimetry, heat lost by a hot body is equal to the heat gained by a cold body, which is expressed as M2 into S2 into T2 minus T3 equals M1 into S1 into T3 minus T1 plus M3 minus M1 into S3 into T3 minus T1. On further simplifying, S2 equals M1 into S1 into T3 minus T1 plus M3 minus M1 into S3 into T3 minus T1 by M2 into T2 minus T3. Matter exists in three states: solids, liquids, and gases. The transition of matter from one state to another is called change of state. The change of state from solid to liquid is called melting, and from liquid to solid it is called fusion. A change of state from liquid to gas is called boiling or vaporization, and from gas to liquid is called condensation. Consider a round bottom flask with a thermometer and steam outlet fixed through the cork. Place some ice cubes at minus 10 degrees centigrade in the flask and start heating. Now, let us observe the change in the temperature of the contents and plot a graph between temperature along the y-axis and time along the x-axis, as it is an independent quantity. Initially, we observe a rise in the temperature of the ice as it absorbs heat energy. This continues till the ice attains a temperature of 0 degrees Celsius. If we continue heating the flask, strangely, we don't observe any rise in the temperature in the ice cubes. But we can observe some of the ice cubes melting. This indicates the change of state of ice to water. And during this process, both solid ice and liquid water coexist. No change in the temperature is observed till the entire ice in the flask melts to water. That means, on absorbing heat, ice at 0 degrees Celsius converts to water at 0 degrees Celsius. The temperature at which the solid and liquid states of a substance are in thermal equilibrium with each other is called melting point. Thus, the melting point of ice is 0 degrees Celsius. In this case, the heat supplied is utilized to increase the internal energy of the substance. The amount of heat absorbed by a unit mass of a substance to convert it completely from one state to another state is called latent heat, usually denoted by L. The word latent means hidden and is derived from the Latin root word latentum, which means to lie hidden. Latent heat is a characteristic of the substance. If Q is the heat required to convert a substance of mass m completely from one state to another at a constant temperature, then Q is equal to the product of m and L, where L is the latent heat of the substance for that particular change of state. The latent heat in the case of solid to liquid transition is called latent heat of fusion, denoted by LF. If we continue heating the water in the flask, its temperature starts rising again and continues to rise to 100 degrees Celsius. As the water gets heated, first, the air that is dissolved in water forms small bubbles at the bottom of the container. After some time, steam bubbles form at the bottom of the flask and move upwards. As they reach the cooler water at the top, they condense and disappear. The process of bubbles of steam forming and reaching the surface intensifies, and we say that the water is boiling. At this point, once again we observe no change in the temperature of the water, even though the water changes to water vapor. Even if we continue heating, the temperature of the water remains constant, and the heat absorbed is used to change the state from liquid to gaseous state. The constant temperature at which the liquid and the vapor states of a substance coexist is called boiling point. The heat required to convert one unit mass of a substance completely from the liquid to gaseous state at its boiling point is called latent heat of vaporization and is denoted by LV. If the rate of heat supplied by the source is known, a temperature time graph can be converted into a temperature heat graph, which is usually called a heating curve. Some parts of the curve are parallel to the x-axis, and some of them are inclined. The inclined portions of the graph correspond to a particular state of the substance. The slopes of the inclined portions are not equal. This means a substance will have different specific heat capacities in different states. The temperatures corresponding to parallel portions of the graph correspond to melting and boiling points. The melting point and boiling point of a substance depends on pressure. If measured at standard atmospheric pressure, they are called normal melting point and normal boiling point. For example, the melting point of ice decreases with an increase in pressure. If a metallic wire with two masses tied to both ends is placed on a slab of ice, we observe it passing through the slab. As the wire exerts pressure, the ice beneath it melts. When the wire passes through, the water above the wire freezes once again. This phenomenon of refreezing is called regulation. In fact, ice skating is possible only because of regulation. When the skaters move on ice, due to the sharp wedges at the bottom of the skates, there is an increase in pressure on the ice, and due to this, the ice beneath melts below its normal melting point. This makes the motion of the skaters smooth and friction-free. The boiling point of water increases with an increase in pressure. To understand this, let us return to the experiment where water was heated in a round-bottomed flask. When the steam outlet is closed, the pressure inside the flask increases, and the boiling point of water also increases. Therefore, the water in the flask stops boiling after some time. After absorbing more heat, the temperature of the water increases to a new boiling point, and it starts boiling again. A pressure cooker works on this principle. When food is cooked in a pressure cooker, the pressure that builds in the cooker increases the boiling point of water to higher than normal. And the food in the cooker is cooked at a higher temperature than if it were cooked outside. This makes cooking quicker and cost-effective. Cooking is difficult in hill stations because at high altitudes, the atmospheric pressure is lower than normal. And as a result, the boiling point of water decreases. Usually, on heating, substances change from solid to liquid and then from liquid to gaseous state. There are certain substances which change from the solid to gaseous state directly. This phenomenon of changing directly from the solid to gaseous state is called sublimation. Dry ice and iodine are some examples of such substances.